Hello, this is Finn, and I'm going to present the proof for proposition 320 of Euclid's elements. There's a few preliminary matters that I want to address before getting into the meat of the proof. First of all, I'm going to be using GeoGebra here with an illustration that I made before. We're going to be using Euclid's elements here. This is a digital copy, so it can be shared on Zoom. This is the exact same stuff that you'll find in the Euclid book that we use in class. And also, for the sake of simplicity, all of the justifications for proposition 320 come from book 1 of Euclid's elements. And so for simplicity, for all the postulates, definitions, common notions, I'm just going to say those things without mentioning which book it comes from. But they're all from book 1, just to clarify. So with that, let's get into the meat of the proof. The proposition 320 states, in a circle, the angle at the center is double of the angle at the circumference when the angles have the same circumference as the base. So right here we have a circle, we have an angle that starts at the center here, and an angle that starts at the circumference here. So according to proposition 320, this angle, the smaller angle, BAC, should be half the size of BEC, or BEC should be 2BAC. Okay. So first step to prove this, join A and E. Right here. And the reason we can do this is because of postulate 1 essentially saying that any 2 points can be joined. Next, extend AE through F. Let's do some fancy GeoGebra stuff here. And the reason we can do this is because of postulate 2, which states that if you have a line, you can extend that straight line in any direction. Next, we have EA here equals EB here. The reason for this is because of the definition of a circle that's found in book 1, definition 15. Because EA and EB are both radii of this circle here, they're going to be equal to each other because all radii of a circle equal each other. Next, because these two segments equal each other, then these angles, EAB and EBA, equal each other. And the reason for this comes from the definition of an isosceles triangle found in proposition 1.5. Basically, that proposition, I can actually pull it up for simplicity. Let's see, 5 here. In isosceles triangles, the angles at the base equal one another. Goes on to say more stuff. This is all we need for the sake of our proof. The angles at the base equal each other. And because in this case, we're dealing with an isosceles triangle, because we have a triangle here that has 2 sides that are equal to each other, then that proposition 1.5 applies, meaning EAB equals EBA. Next, EAB plus EBA equals EAB plus EAB, or 2EAB. The reason for this is common notion 2. If equals be added to equals, the sums are equal. We already established that these 2 angles here equal each other. And so 2 of one of them equals the sum of the 2 of them because of common notion 2. Next, BEF equals EAB plus EBA. Now, this is probably the most complicated justification in this proof, so I'm going to pull up the actual reason for this, which is proposition 132. Let's go back. 132 is dealing with triangles. In any triangle, if one of the sides is produced, then the exterior angle equals the sum of the 2 interior and opposite angles, and the sum of the 3 interior angles of the triangle equals 2 right angles. The only part we need is this part here. If any triangle is produced, well, in any triangle, if one of the sides is produced, then the exterior angle equals the sum of the two interior and opposite angles. So in this case, we have a triangle, EAB. One of its sides is produced. AE is produced to EF. So then, if postulate 132 holds, then this angle here, BEF, this is the exterior angle, should equal the two interior angles, EAB plus EBA. And the reason for that, again, is because of proposition 132. Okay, so because we know that's true, then we also know that BEF equals 2 EAB. And this is because of common notion 1. If equals be added to equals, the sums are equal. So this is, it's kind of hard to remember because you can't see that I have this written down. But basically, we already proved that EAB plus EBA equals 2 EAB. And because we also know that BEF equals EAB plus EBA. Therefore, because 2 EAB equals the exact same thing as BEF equals, then those two things equal each other. If things equal the same thing, then they equal each other. That's common notion 1. So the conclusion of that is BEF equals 2 EAB. And then we've been dealing up until this point with one half of this triangle here. We haven't talked about the top half. Euclid talks about it briefly, but he doesn't go through all the same steps as he does for the bottom half because it's basically the exact same thing. So in Euclid, it says, for the same reason, FEC equals 2 EAC. So basically, the reason for this is if BEF equals 2 BAF, then the opposite side of this circle here is the same thing is going to apply. Okay, and then for our final thing, we know, because of all the things that we've proved before, that BEC equals 2 BAC. And this is fairly simple because if we've proved that FEC equals 2 FAC and BEF equals 2 BAF, then those things added together, BEC equals 2 BAC. And that's what we set up to prove from the beginning. So our proof is completed. I hope that was helpful.